Hello once again. Let's do review sheet 3 from the fall semester on physics. And this might get a little bit long, so I'm going to do this in two parts. Do the first 2 pages and then do a separate video for the last 2 pages. And this was the unit where it really got challenging because the second unit, when we introduced kinematics, it was kind of just learning how to solve problems, plug numbers into equations, knowing the difference between vectors and scalars, all that stuff. Here we're doing forces, we're doing momentum, we're doing impulse, we're learning about friction and air resistance. A lot of things going on here. In fact, I'm going to go back in the midst of doing these problems and go redo a few sheets that we did when we were learning those topics. So I'll kind of interrupt this sheet to review some ideas. But a little bit of encouragement here is remember that the physics portion of the final exam will only be 50 questions. And we did about 4.5 units in the fall on physics. I say half because the last unit was that little short unit on waves. So if you take 4.5 units and you have 50 questions, they're not going to be more than maybe 15 questions per unit. So despite there being 37 questions on this review sheet, you're not going to get 37 questions on this Unit 3 material of forces and such. You might get, like I said, like 15 questions. So don't freak out. You're not going to be expected to answer so many questions. All right, let's get started. So number 1, the box has a weight of 10 newtons. The hand is pushing down on it with 5 newtons. Draw an arrow for the weight. So again, I'm not happy with the way I wrote this review sheet. I just kind of start with a topic we get into a little bit later, including that third law, that second part of this problem. So kind of excuse me that it's not really scaffolded well. But let's just start doing it. So the weight of an object is how hard the earth is pulling down on it. So it's a force. It's the force of earth on the object, assuming we're talking about being on earth. So the weight of the box is 10 newtons. That means the earth is pulling down on it with 10 newtons. So we're going to draw an arrow to represent the weight of the box, okay? And it says label it. So remember that our symbol for weight is F sub G. We said it's 10 newtons. That means the force due to gravity, how hard gravity is, or how hard the earth is pulling on it, which is the force of gravity. Draw an arrow for the force of the hand on the box. We'll use a different color. And so the hand is pushing down on the box with 5 newtons. So I'll do this in green, and it should be about half the size, right? Make that a little darker. So I'm just going to call this, as no standard symbol, force of hand, how hard the hand is pushing, and that's 5 newtons. Remember, newtons is the SI unit of force or weight. C, the box is not accelerating, so what must be the normal force? Well, I'm going to back up a little bit, and there's something important that comes up frequently when we deal with forces. Remember that the symbol for net force is sigma F. That's a kind of a bad sigma. When the net force is 0, meaning all the forces cancel each other on the object, the first thing you should think of is that velocity is constant. In other words, the acceleration is 0. It's not changing velocity. But the converse is true as well, if that's the right word, is if the velocity is constant, if it's not accelerating, if it's not changing velocity, that must mean the net force equals 0. So going back to the problem, I said the box is not accelerating. Obviously, it's just sitting there against the ground. So what must the normal force? Well, let me ask a question before that. What must be the net force on the box, the sigma F, if it's not accelerating? 0, right? So the other force acting on it is the normal force. And again, I didn't do these questions in a good order. I haven't even introduced the normal force on this review sheet. The normal force is the force of a surface pushing on an object. In fact, let's go interrupt myself and go to number 2 there and just draw those. So here's a box against the ceiling on number 2. Draw the normal force. That normal force is what I was calling the you can't go through me force, or I like to call it get away from me force. So when the box is being pushed up against that ceiling, the ceiling is like, no, you don't. You're not going to go through me. I'm going to push back against you. And so that is the normal force, which we use F subscript capital N for the normal force. The normal force, the term normal means perpendicular. The normal force is always away from the surface that's exerting the force, perpendicular to the surface. So this one to the right, which way is the normal force? That way. It's perpendicular to the surface. That's the surface right there. Not the surface of the object, but the surface of the object that's pushing against the box. And so that's the normal force. So yeah, that's the idea, is the normal force is the force that some surface, table, ground, wall, ceiling, whatever, the force it's pushing against an object that's pressed up against it. So our normal force is going to be on the box, back in the previous problem, upwards, away from the surface. But this finally gets to the question numerically. We said the net force must be 0 because it's not accelerating. But notice that there's right now 15 newtons of force going down on the box. So if it's not moving, if the net force is 0, how big must the normal force be? 15 newtons up, right? And so when you were drawing forces, we had to make the arrow long enough, because if you added those red and green arrows, it might be as long as that magenta arrow. So the normal force, that's not a very good F, is equal to 15 newtons. Okay. So now you look at that and go, oh, net force is 0, the box is not accelerating. Draw an arrow for net force and label it. We just did that. Now again, here we are jumping to the third law. Shouldn't have done that right away. So let's go ahead and interrupt. If you want to skip this and just go back to the question, scrub ahead, and then and find where I'm going to number 2. But let's get to this worksheet we did earlier. In fact, I'm going to just give the answer key just so I can go a little quicker. So Newton's third law is a really tough concept. It sounds so simple, but when you ask questions, people just have a little trouble with it. So Newton's third law is that whole idea that for every force, there's an equal and opposite force. If I push you, you're pushing me. If I push down on the table's pushing back on me. If a ball hits a ceiling, the ceiling's hitting the ball. It takes 2 to tango. If something's exerting a force, using a letter, if A is exerting a force on B, B is exerting a force back on A of the same size but opposite direction. So let me go ahead and just, I thought I had something for pointing. Maybe this. I won't draw on this, but look at this one right here. Yeah, that's the one. I was trying to remember if that's the thing that kind of goes away. I'm just playing around, okay? Sorry. So here's a kid, and I'm saying the kid's pushing on the wall to the right with 40 newtons of force. So if the kid's pushing on the wall with 40 newtons, or 40 pounds, how hard is the wall pushing on the kid? 40 pounds. That is essentially what the third law is. The wall can't push with a different force on the kid than the kid's pushing on the wall. They must be equal and opposite. Now, of course, on the final, you're not going to have to draw these arrows, but I hope when you look at that, it kind of makes sense. The kid's pushing on the wall, but the wall is pushing back on the kid with the same exact 40 pounds of force. They're a third law pair, an action-reaction pair. Let's, again, I'm just kind of skipping some of this. Let's go to, I'm just going to make that little highlight a little bit smaller. Okay, I can't. Okay, so let's go to that face, the fist being punched by the face. So it says the fist punches the face to the left with 100 newtons of force. Well, how hard is the face pushing on the fist? 100 newtons of force in the opposite direction. So remember that the way I told you that you can identify the action and reaction, it's kind of easy here with only 2 forces, is notice the way I term this. This is force of fist on face. That makes sense? So the reaction is you just change those 2 nouns. The reaction is force of face on fist, how hard the face is pushing on the fist. Okay, let's keep going. So I don't want to drag this on too long. So let's do the dart gun. And this kind of explains recoil like we talked about in class long ago. So the Nerf gun is pushing on the dart with 5 newtons of force. So force of gun on dart is 5 newtons. Well, how hard is the dart going to push back on the gun? 5 newtons of force. Force of dart on gun, you just reverse those nouns. The two objects that are interacting with the same force, but just opposite direction. So that's why you feel a little bit of a recoil, because the gun is exerting a force on the exiting bullet or the dart, and that dart is pushing back in the other direction against your hand. Okay, let's do, what's down there? Oh yeah, I guess it's a pretty long sheet. I'll try to hurry a little bit. So let's do a refrigerator and a magnet. So these are moving towards each other. The refrigerator is the magnet's pulling on the refrigerator with 3 pounds of force. So that means the refrigerator's pulling on the magnet with 3 pounds of force. Okay, again, I'll go really quick. How about a backpack hitting the floor, or sitting on the floor, I should say? Well, the backpack pushes down on the floor with 80 newtons of force. So how hard is the floor pushing up on the backpack? 80 newtons of force. They're a pair. Force of floor on backpack, force of backpack on floor, equal and opposite. And how about this one? The weight of the kid. So the weight, remember, is how hard the earth is pulling on you. So your weight is a force being applied to you by the planet. So if the earth pulls down on the kid with 100 pounds of force, that's his weight. So there's the force of earth on kid, his weight basically. But the reaction is force of kid on earth. You just switch the nouns. If the earth is pulling on the kid with 100 pounds of force, the kid is pulling upwards on the earth with 100 pounds of force. It's just, he's not going to cause the earth to move very much. Okay, so just kind of to finish these, and then this is kind of my classic one here. And again, don't worry about this. I'll probably have 1 or 2 at most third law problems. So if you don't get it, you're not going to suddenly get an F on the final because of this. So that's why I'm kind of hurrying. I don't want to overemphasize this. So back to the backpack one. Remember that we call the force of a, I thought I had the answers there. Maybe that's just over here. The normal force, that's the force of the surface on an object that's pressed up against the surface. So back in example 5, I said that the backpack is pushing on the floor with 80 newtons. And the way I asked it was, well, how hard is the floor pushing up on the backpack? 80 newtons. I might have asked it the other way. But that's just the normal force. So if I did ask it that way, if I said the floor is pushing down on the backpack with 80 newtons, what's the normal force? Well, that's me asking how hard is the floor pushing up on the backpack. But I actually think the way I asked it was, how did I ask it? I did say that, but maybe I'm just reversing this. If I told you the normal force on the backpack is 80 newtons, and I said, well, how hard is the backpack pushing on the floor? Well, that normal force is describing how hard the floor is pushing on the backpack, so therefore the backpack must be pushing on the floor with 80 newtons. Or again, kind of hurrying a little bit here, is the weight of the kid. If I gave you the weight of the kid is 100 pounds, that's how hard the earth is pulling down on the kid. That's his weight. So that means he's pulling up on the earth with 100 pounds of force. That's an action-reaction pair. I'll kind of skip that. And then again, maybe I'll skip that. I'll let you read it if you want. But here's kind of a classic question. We'll see this repeated in the review sheet or variation. The box has a weight of 20 newtons. That's this thing here, obsession cover. Let me go back to my pen. So there's the weight, the 20 newtons. The hand is pushing down on it with 30 newtons. I called it this time force of push or pushing force, or it could be force of hand. And the normal force is 50 newtons. That's that one. So those are the 3 forces acting on the box. So each one of these is going to have a reaction to that action force. So this question says, force of push, this thing down here, is how hard the hand is pushing down on the box. So how hard is the box pushing up on the hand? 30 newtons. They're the same. I could draw an arrow on the hand of 30 newtons. Okay, sorry, I'm just being a little sloppy here. F sub g is how hard the earth is pulling down on the box, its weight. So that's the force of earth on the box. So how hard is the box pulling up on the earth? 20 newtons. It's the reaction. F sub n, the normal force, is how hard the ground is pushing up on the box. So how hard is the box pushing down on the ground? 50 newtons, same value. Okay, so sorry about that, but I don't mean to waste your time, but I just kind of want to go over that. Again, I'm going to guess there's probably one third law question on the final, but maybe there's two. So let's think about the third law here. How hard is in letter E, how hard is the box pulling up on the earth? Well, I'm looking for force of box on earth. Well, what is the pair for that? The other part of the pair is how hard the earth is pulling down on the box. Which one of those three forces I drew represents the force of the earth pulling down on the box? That one, right? 10 newtons. Those are a pair. How hard is the box pushing up on the hand? Well, if the hand is pushing down on the box with 5 newtons, how hard is the box pushing up on the hand? 5 newtons. How hard is the box pushing down on the ground? Okay, that's a little bit trickier. So I'm looking for how hard the box is pushing down the ground, but to figure that out, I need to know how hard the ground is pushing up on the box. Well, which of those three represents the force of the ground pushing up on the box? That one. So it's 15 newtons. Okay, again, I apologize for spending so much time going over that, but some of you might find it useful. Let me go ahead and erase this to get out of the way for the next problems. Okay, let's move on to number 3. A 5 Newton ball is slamming into the ground and slowing down. Is 5 newtons its mass or its weight? So basic things. We haven't practiced this in a while. We haven't done forces. Newton is a unit of force or weight, because weight is just a type of force. So that's weight. Mass would be for SI, kilograms. In imperial, it would be slugs. Draw the force arrow for the weight. So remember, the weight is the force the earth is pulling down on an object. So if it weighs 5 newtons, we're going to draw F sub G downwards, kind of sloppy arrow, and say it's 5 newtons. That's the weight of the ball. What direction is the net force? Now here I'm going, that's part C. Let me go off on a little tangent again and remind you of some things. Having a force that's positive or negative or to the north or to the south, is not necessarily meaning that it's going to speed up or slow down. Whether something speeds up or slows down depends on how the direction of the net force compares to the direction that it's currently going. So you tell me the answers to this. Let's say an object, its velocity is to the right. So there's some object here, I'll just do like a box, just to the right. And let's say the net force is to the right. Let's say net force is right. What's going to happen to the speed of that box? It speeds up, right? What if I said the net force is to the left while that box is heading to the right? It slows down, right? Let's try it another one. Let's go up and down. Let's say this box is going upwards. That's its velocity. So that's not a force arrow. I'm just saying its velocity is upwards. I'll switch it. If the box is slowing down as it's moving up, which way is the net force? The net force must be down. Again, the idea is if something is slowing down, the net force must be in the opposite direction that the object is currently going. If the net force were up while the box is moving up, what would we see happen to its velocity? It would speed up, right? And maybe I could just switch it another way. Let's say that I have some box again, and I know the net force is to the right. Again, we don't draw net forces on objects, so that arrow doesn't mean anything. But let's say the net force is to the right. And now I'm going to say that the object is slowing down, that box is slowing down. Okay? So if the net force is to the right and it's slowing down, which way is the box currently moving? It must be moving to the left, right? And that kind of makes sense. If it's moving to the left and the net force is to the right, that means the object slows down. Okay, so that's kind of an important point. Again, will that come into play on the final with the few questions I have to ask about this stuff? Maybe not, but I tend to try to hit it at least once. So let's see how that's relevant to question number 3. What is the direction of the net force? So notice what's happening. The ball is slamming into the ground. You see the motion lines. Well, what's happening? I actually said slowing down, but you could have guessed as it's slamming into the ground, it must be slowing down. So the velocity is downwards, but it's slowing down, right? That makes sense? The velocity is heading down. It hasn't, it's going to be compressed before it springs back up off the ground. It's moving downwards and it's slowing down. So which way must the net force be on it? The net force must be up, right? That makes sense? So if something is moving down and slowing down, the net force must be up. And so that's the answer to this one. So what is the other force acting on this ball other than gravity? 5 newtons, its weight. Well, whenever something is in contact with a surface, like a table, a wall, a ceiling, the floor, there's a normal force exerted by that surface on that object. So there's a normal force on that ball. And which way is the normal force going to be? It's always away from the surface, perpendicular to the surface. So without finishing it yet, we know there must be a normal force in that direction. It's always away from the surface. But we just said that the net force is up. So how big must the normal force be compared to the weight of the ball to allow the net force to be up? It must be bigger than 5 newtons. And so I don't know exactly how big, but I need to draw my arrow bigger than the 5 Newton arrow. Not easy, especially since we really haven't practiced this. And we worked our way up to an understanding of that last semester, and you guys were awesome. But I know it's just, don't feel bad. When I look back at these review sheets, I'm like, wait, how do you do this problem again? So they're not particularly easy. So if you find yourself a little confused, you're not alone, and that doesn't mean that you're not the incredibly smart person you are. It's just that we haven't practiced this in a while. Okay, let's go to number 4, which is actually, again, I didn't order these very well, did I? This is actually what I was just talking about. If the net force is to the north, actually, there's something additional here. The acceleration is to the north. I'll come back and explain that. And the change in velocity is to the north. Again, I'll come back and explain that. But here's the thing that I just already mentioned. It also means that if it is actually moving to the north, the object will speed up. So again, that's the idea that if the net force is to the north and it's moving to the north, that means it'll speed up. If the net force is to the north, and let's say it was moving to the south, it would slow down. So those first 2 questions, what do those mean? Again, it's not going to be that important for the final. But remember that the net force, one of the new equations we learned, is the mass of the object times its acceleration. So this is a vector. Might as well remember that. All forces are, well, not all forces, I shouldn't say that. We don't think weight as a vector, even though weight is a force. We kind of treat weight as a, well, I guess it is. I'd get myself in trouble if I said it's not a vector, because it is pointing towards the center of the earth. But all weight is towards the center of the earth, so we kind of don't even think of it that much. But it does have a direction, so weight is a vector. And then we have the acceleration, which is a vector. So vectors are directions. Now notice I have one direction on the left, one direction on the right. They have to match. So if the acceleration's to the north, I'm just multiplying it by a scalar mass. Which way does the net force have to be? To the north. The same thing with this equation, which we learned last unit. The change in velocity is a vector, the acceleration is a vector, and times a scalar. So if the acceleration's to the north, what does the change in velocity have to be? To the north. So again, I don't think that's a very important question. So it's kind of just ignore that. That will probably not come up. Let's do number 5, which brings back a little bit of kinematics with forces. So no, you don't have to use DESPA. We're just doing multiple choice. But I'm going to show a little bit of work just to show you how you could solve the problem. Now keep in mind, we have 100 questions, multiple choice, in 120 minutes. That's a little over a minute per question. But there can be some questions that might take you 4 or 5 minutes, because many of the questions should take you like under 30 seconds. So there will be some times where you might have to do a little bit of work. So don't panic if you're spending like 5 minutes on a big calculation question. We take that into account. So let's go ahead and do this. Going and reading the question, notice it's mentioning west. Well, as you know, we learned a way that we often have the standard practice of just declaring which way is positive. So we're going to call west positive since it mentions a lot of west. Fine to call east positive if you want, but we'll call west positive. So let's write down the given information. That's the D, the data. It really helps you a lot. So don't spend a lot of time, but just let's do it. So the initial velocity is the 30 meters per second, right? And since it's to the west, it's just positive. The final velocity is 10 meters per second. Again, it's positive. The time is 4 seconds. And the mass is 1,000 kilograms. So that's kind of weird. We're so used to just kinematic equations without problems without masses thrown in. And we're looking for the net force. It's always nice to write down what you're looking for. Okay. So again, a lot of problem solving in physics is you write down the given information with the symbols and you look for an equation that you can use to solve this. Okay. Now I mentioned that, if you're kind of lost and you're not sure what to do, you could just do one of two techniques. You could kind of do forward thinking. So for example, if I'm trying to find the net force, which equation am I going to use? Well, the one equation that we have with net force in it is net force equals mass times acceleration. So then you can kind of do some planning. You can say, well, I got the mass, check, that's over here. So if I can get the acceleration, I can finish this problem. So it comes down to somehow finding the acceleration from this information and then multiplying it by the mass. Now, that's fine, but again, another technique you can have is saying, well, I'm totally lost. I have no idea, but I just want to get some partial credit, as if this were a test where you can get partial credit. And you say, let me just solve for something. Let's see what it can solve for. So let's do that method. All right, so looking at the given information, notice I give you an initial velocity and a final velocity. And I try to teach you, whenever you see initial and final velocity, what two velocities can you solve for? You can solve for v average, right? And you can also solve for the change in velocity. So let's think about that. Well, v average, we use that in this equation, delta x equals v average t. Yeah, we can solve for v average, and we're given the t, so we can actually get the delta x from this, the change in position. But is that going to help me find the net force? Not really. So what about delta v equals at? That's the equation that we often use for this stuff with forces and stuff, because it's going to change velocity. Well, we can get the delta v, and we're given to, we can solve for a. And if we can solve for a, we can multiply it by the mass and get the net force. Cool, let's do that. So we don't need to do that. So what we do is first find the change in velocity. The change in velocity is just the final minus the initial velocity. The final is 10 meters per second. It was positive because it was to the west. And the initial was 30 meters per second. Again, you don't have to show this work on the final. I'm not going to see it. I'm just going to see your Scantron. So negative 20 meters per second. And now we're solving for the acceleration using that equation. So negative 20 meters per second. The time is 4 seconds. So negative 5 meters per second squared. Or you can just leave it meters per second. Now we just take the mass, multiply it by negative 5 meters per second squared, and we get negative 5,000. And then the unit becomes, despite my sloppiness, kilograms meters over second squared. And wait, do you remember what that is? What's a kilogram meter per second squared? That's a Newton. Unsurprisingly, because we're solving for a force, and notice that we're using SI units everywhere. Do you remember what a pound really is? A pound really is a slug foot per second squared. Okay, I'll go ahead and erase those things. So we solved it. Cool. Now, again, this is not easy. You haven't done this in a long time. You got good at these questions. So you guys are smart. So don't feel bad if this is confusing. We haven't done this type of problem. We haven't done physics in so long that you're just a little rusty. I'm a little rusty going back and doing these problems. So don't kick yourself if you're not being able to get this right away. It's just not really current on your mind. It's kind of ancient history for you now. So you'll get it. All right, let's do number 6. I think we're okay with that one. All right. On a roller coaster, a kid accelerates at 20 feet per second squared. Accelerations are often written as a distance unit over time unit squared. That's how we kind of identified that. The kid is 2 slugs / 64 pounds. I gave you both his mass and his weight because I'm going to give you an option on what you're going to do to solve this. What's the net force on him? Just to change color, let's try orange. So the net force, remember, is sigma F, and it's just the mass times the acceleration. So we're given the acceleration, but now which of those two values am I going to put in there? 2 slug or 64 pound? Well, I need the mass. Which of those is mass? The 2 slug. So it's just a way of saying, just use mass in that equation. Don't use weights. So it would be 2 slug, or 2 slugs, times 20 feet per second squared. And that's what I was just mentioning before. If you remembered what a pound was, you don't need to put it in pounds, but that's 40 slug feet per second squared, which is the same thing as 40 pounds. Okay. Just a quick little question just to kind of clarify that, slug is the mass in imperial units, pound is the weight. Okay. Number 7, the block is moving to the right and slowing. Oh, this is like what I was talking about before. So if I'm asking it multiple times, maybe it will be on the final. The block is moving to the right. So maybe I'll even right there, just remind me, the velocity is to the right. And slowing down with an acceleration of 20 meters per second squared. What is its mass? Well, maybe just, if it becomes relevant, deal with it now. If it's moving to the right and slowing down, what is the direction of the net force? The direction of the net force must be to the left, because if something's moving to the right and slowing down, the net force must. But I guess I didn't need that because I gave you the 2 forces in the diagram. We can see the net force is to the left. All right, so we're looking for the mass, so we're going to end up just doing mass equals net force over acceleration, right? Not a difficult problem, is it? We're going to take the net force, which is 5 newtons, and I'll just say to the left, an L there. And the acceleration is 20 meters per second squared, right? Now, what's the direction of this? Actually, I didn't say, but the acceleration must be to the left, because if the net force is to the left, then the acceleration has to be the left. So it's kind of useless that I wrote L up there, as they were going to be in the same direction no matter what. And they have to, because they need to cancel. If you could cancel direction, it doesn't really make sense, because mass is a scalar. I couldn't have a net force to the left and an acceleration to the right. That wouldn't make sense. So basically, it's just going to be 1/4, so 0.25. But what is the unit for this? Well, here's the easy way. I was using SI units for the force, 5 newtons, SI units for acceleration. So what should I get for the units for mass? The SI units. Kilograms. I hope that kind of made sense. Now, if you weren't sure about that, you could rewrite Newton as kg m per s squared, and you can see that this m per s squared will cancel this m per s squared, and you're left with kilograms. All right, number 8. A 10 kilogram crate, that's its mass, because I'm giving you kilograms, not newtons. If I said 10 newtons, that would be its weight. A 10 kilogram crate is initially moving to the right at 5 meters per second. Then it experiences the forces shown. What velocity will it have 3 seconds later? And again, I'm just saying, hey, you're lost. Let's just solve for something. So let's write that down. We got a mass of 10 kg. We got an initial velocity of 5 meters per second to the right. I'll just go ahead and say right is positive, okay? Then it experienced the forces shown. And let's just go ahead and say what the net force is. We can get the net force not just by using net force equals ma, but from diagrams. So the net force is 20 newtons to the right, which we already identified as being positive. So we'll just do positive. And we're looking for the final velocity, because it started at some initial velocity of 5, but we want to know what velocity we'll have 3 seconds later. Oops, we got one more piece of information, 3 seconds. All right, so let's not give up. And again, same thing with me. I'm doing this problem now. I'm going, okay, what am I going to do here? Again, a couple of strategies is, saying what I'm going to try to achieve, like looking in the future, how am I going to get the answer? But let me do that other strategy. Like, what can I solve for? I'm totally lost. Let me solve for something. Let me look for partial credit. So notice I'm given a net force and I'm given a mass. what can I solve for? Even if I don't know how that's going to get me the answer, for partial credit, if this were a test where you get partial credit, what can I solve for? Acceleration, right? So let's go ahead and do that and see where it leads. The acceleration is the net force over the mass. It's 20 newtons over the mass, which is 10 kilograms. And that's going to be 2. Now, again, we could trust that if we're keeping SI units everywhere, we're going to get the SI unit for acceleration, which is meters per second squared. But you want to see how it works. A newton is a kilogram per second squared. So the kilogram will cancel that kilogram, and we're left with meters per second squared. Now we say, okay, what am I going to do now? I have acceleration. How am I going to get to final velocity? Well, think of another equation we have. We have delta V equals AT. We have A that we just solved for. We have T. So what can we solve for? Delta V. Let's do it. Who knows where it's going to lead? But let me just get some partial credit. So the acceleration is 2 meters per second squared. Sorry, I'm talking fast. I'm just trying to hurry up a little bit. I wanted to get through the first 2 pages in an hour. I don't know if that's going to happen. And the time is 3 seconds. So this is going to be 6 meters per second, because the seconds of the time is going to cancel one of those seconds. Now we say, okay, what do? I got a change in velocity. They want to know the final velocity. Oh, well, that's simple. I know the initial is 5, and it's changing by 6, positive 6. So what's the final velocity? 11. Now, if you want to be a completist, you could say the final velocity is the initial plus the change. So again, you're taking your 5 meters per second initial velocity, and you're going to add to it the 6, and you get 11 meters per second. Again, as I said, you guys are fantastic. 8th graders who are doing problems like this, you guys should be very proud of yourself. Okay, let me erase that, and we'll do the next one. Oops, I didn't get the erase button. All right, let's do this one. These will be a little bit quicker, not so much explanation. What color do you guys want? Let's see if we get the other color. Where are my other colors? I forgot where my colors went. Usually you can press on something. I don't know what's going on. I'll just use the colors here. I like that blue. What is the weight? You're thinking, this guy losing his mind. What is the weight of a 10 kilogram backpack? Quick little lesson. Well, not really a lesson, just a formula. The weight, I'm using F sub G. Some people use W for weight, but I use, to keep my forces all consistent, it's going to be capital F subscript something. So the force due to gravity, the weight, is the mass times the acceleration due to gravity for that planet. And so we're just going to assume it's Earth unless I say it's otherwise. And we're rounding off. Remember, the G on Earth, we're going to say is 10 meters per second squared. Actually, 9.8, but we'll just use 10. Or if you're using imperial units, 32 feet per second squared. So we need to multiply the mass, 10 kilograms, times the acceleration due to gravity, which is 10. We're going to use that version because I'm using SI mass, so use SI acceleration due to gravity. And you get 100 kgm per s squared, which is a Newton, right? What is the weight of a 0.1 slug textbook? Slug is a mass. Remember that, so you're not thinking this is a weight. So the weight of an object, again, is the mass times the acceleration due to gravity. But since I'm using imperial mass, I want to use the imperial version for the acceleration due to gravity, and you get 3.2 slug feet per second squared, which is the same thing as a pound. Good, I'm doing some questions without so much talking. You're probably enjoying that. What is the mass of a 0.15 Newton pencil? So that's a force unit or a weight. So the mass is just going to be the weight divided by the acceleration due to gravity. That's subscript G. That's the actual big G, well, not big G, but the normal size font G for the acceleration due to gravity. So the weight is 0.15 newtons. And then what is the acceleration due to gravity? Well, I'm using SI there, so let me use the SI version. And so 0.15 divided by 10 is 0.015. Now, what's the unit for this? Well, again, trust. We're using SI units everywhere appropriately, newtons and meters per second squared, and I have the formula right. So what do you think the mass unit is? Kilogram. or you can cancel if you change Newton to kilogram meter per second squared. What is the mass of a 3,200 pound car? I won't rewrite the formula. We take the weight, 3,200 pounds, but now since we're using imperial weight, we're going to use the imperial version of the acceleration due to gravity. And again, we'll trust, it's going to be 100, right? We'll trust that if we're using imperial everywhere and we have the right formula, we're going to get the imperial unit of mass, which is slugs. Yeah, again, that's a car, sure, but remember, a slug is a lot of mass. Number 11, if the block is currently moving to the right, okay, so this is that idea again. I think I'm overdoing it on this type of question. The block is moving to the right, what will happen? So notice that the net force is which direction? To the left, right? I don't know why I'm writing on the right, but the net force is to the left. So again, if it's moving to the right and the net force is to the left, it will slow down. Yeah. A 2 Newton ball, that's its weight, because I'm giving newtons, not kilograms, is slamming into the ceiling and slowing down. Draw the two forces acting on the ball, F sub g, its weight, and F sub n, the normal force. And, so we don't know how big the normal force is yet. We're just going to do a placeholder. So the weight is always how hard the earth is pulling down on it. So there is the weight. And we were given that it's 2 newtons, so we'll go ahead and fill that in. Okay, that's weight. It's always pointing towards the ground. That's F sub g. Now, let's think about the normal force. It's going to be pointing which direction? Down. Not that the normal force is always down. I don't mean to say that. But it's always away from the surface. So the ball is hitting the ceiling, so the normal force is going to be down. Now, again, I don't know how long the arrow will be, so I just won't put the arrowhead yet. We want to make it relative to the 2 newtons. So we know it's going to be that direction somehow. I'll go ahead and put in just F sub n, and we'll fill in the value later if we find it. So part B, we actually do a calculation. It has an acceleration of 40 meters per second squared down. What is the normal force on the ball? We don't have an equation for the normal force. We just have an equation for the net force. So how do we find this? Well, we know the net force equals ma. If we knew the acceleration, we do. We could find the net force if we know what other property? The mass. So somehow we got to find the mass, because I could use that acceleration with the mass to find the net force. I know this is kind of long here, but then once I get the net force, I can logically figure out what the normal force is. But the first thing was to find the net force, because I don't have an equation that's like the normal force equals something, something, something. So we always get the normal force just by looking at all the other forces acting on the object and logically figuring out what the normal force must be. So how do I get the mass? Well, similar to those problems up here, all we have to do is use the weight, 2 newtons, and the acceleration due to gravity to solve for the mass of the ball. So as a little detour here, we know the mass of an object is its weight divided by the acceleration due to gravity. And we were told the weight is 2 newtons, and the acceleration due to gravity is 10 meters per second squared. So we get 0.2. What do you think the unit is if we're doing mass and we're using SI units? Kilograms. So now we can solve for the net force. My sigmas are terrible today. 0.2 kilograms times the acceleration, which we said is 40 meters per second squared. I'll just put down. I won't worry about positive or negative here. So when you multiply 0.2 times 40, you get 8 kilogram meters per second squared, or newtons down. Okay, that's not the answer. That's the net force that we're getting. We were asked for what is the normal force on the ball. So, but let's go back to our diagram. We know the net force is 8 newtons down. We already have 2 newtons down due to the weight of the ball. So how big must the normal force be? 6 newtons, right? And because I made that arrow so long, if I want to do them proportionally, there is my normal force. Now you can see that if the weight is 2 newtons down and the normal force is 6 newtons down, the net force is 8 newtons down, which is actually what we calculated. So again, if you're finding a normal force, usually you find the net force, and then just by looking at your diagram at the other forces, you figure out, adding or subtracting what the normal force should be. Okay, let's move on. 13. Hopefully some of these, this will take a little bit, I might jump around on this, I don't know, because there's some little sheets we're going to review. So let's review some friction stuff. I put that little worksheet that we did in class with that cow, okay? So let's go ahead and do this really quickly, and this might be a good reminder because, again, you guys got really good at these and always got them right. And it's just because we were doing them currently. It's been a while. So let's look at this cow. You're pushing with 5 newtons of force to the right, but the cow does not move. Well, what does that say about the net force, the sigma F? Remember, if the velocity is not changing, the net force must be 0. Or saying it another way, if the velocity is constant, the net force equals 0. Or if there's no acceleration, the net force equals 0. So the net force is 0. So how big must friction be? Well, if the net force is 0, the friction force must also, if the net force is 0, the friction force must be also 3 pounds. And in our class, we're using F sub F for friction is 3 pounds. And so now, that's why the cow doesn't accelerate, because we're pushing with 3 pounds, but the friction is pushing back with 3 pounds. It's meeting our push. Number 2, we want to get this cow moving, so we decide to push with 10 pounds, but the cow still doesn't budge. Well, is the cow accelerating? No. So what must be the net force? 0. But if the net force is 0, how big is the friction force now? 10 pounds. And that's why it's not accelerating. So that's the big thing about what we call static friction. Static friction is friction when the object is not moving. Static friction can grow to match your push. It's variable. It could, if you push harder, it gets bigger and bigger. But there's a maximum that it could achieve. But again, just reviewing, notice how the static friction force grew from 3 to 10. And maybe if I push with 12 pounds, friction will still be 12 pounds to match me. Or not still be, but it'll be 12 pounds to match me, and so on. But it can only be a maximum. At some point, you overcome friction and you can get that cow to slide along the surface. So that's what we're jumping to in number 4. I missed number 3 somewhere. Is we got the cow moving. There's its motion lines as I'm pushing with 16 pounds. But notice I'm saying when I'm pushing with 16 pounds, the velocity is constant. So what is the net force? 0, right? Because if it's constant velocity, the first thing that goes in your mind is net force equals 0. So if the net force is 0, what must be the friction force to the left? 16 pounds. That's the only way. I'm not sure if that arrow is the same length. So now it's 16 pounds. So this is what we call kinetic friction or sliding friction. Friction when the object is actually moving along the surface. And here's the important point and an important difference between static friction and kinetic. Static friction will change its value as you push harder and harder. It could grow to match your push up to a certain max, and then it just kind of gives out. But kinetic friction stays constant the entire time. So if you push harder, if you push less hard, if you let go, as long as that cow is moving, there's going to be 16 pounds of frictional force on it. So that's the big idea. Kinetic friction stays the same. So problem 5, let's say that I get a little tired and instead of pushing with 16 pounds, I say I'm going to only push with 15 pounds. Well, what's going to be the frictional force? Did you say 15? Then you're wrong. It's 16 pounds. So think about what I just said or read that little paragraph. It doesn't matter what I do. If the cow is sliding, that kinetic friction force will remain a constant 16 pounds of force. That's why the cow will slow down. So from practical experience, let's say you're pushing a shopping cart, and then you're pushing at constant velocity while you're pushing with 16 pounds. And now let's say you push a little less hard. Well, what happens to the speed of the cart? It kind of quickly slows down and stops, right? And that's because there's a net force in the opposite direction you're moving because you push less hard, but friction remains the same value. I don't mean to go off on such a tangent, but yeah, kinetic friction stays the same value. Number 6, the cow was sliding along and we stopped pushing altogether. And I was looking at this and I'm thinking it should have been ALTOGETHER, one word as opposed to all together. The cow will slow down and stop. While this is happening, so while it's sliding, but before it comes to a stop, which direction must the net force be? Well, it's going to be in the opposite direction the cow is moving. Again, that idea that if the cow is moving to the right and slowing down, the net force must be to the left. Now, how big is friction? Did you get this? 16 pounds. So again, as long as we identified from this problem that by pushing at a constant velocity, that the frictional force is 16 pounds. So as long as the cow keeps moving and doesn't stop, friction will remain 16 pounds. And that allows the cow to eventually stop by having this single force, 16 pounds, to the left to slow it down. So when an object is sliding, friction is constant. When it's not sliding, when it's standing still, that's static friction that can vary. Now, I probably won't ask you about this, so I'm not going to spend time on this last thing. But just if you're wondering, that's this whole idea where, let me use the analogy. You're pushing on a sofa in your living room trying to move it. And you're pushing harder and harder. You can't get it to move. And then finally, it starts to slide. And do you recall, do you have that experience that once you get it sliding, it actually slides across the carpet much more easily, right? So that's the idea that static friction can keep growing higher and higher. So maybe as I'm pushing this cow, I'm pushing with 11 pounds, 12 pounds, 15 pounds, 25 pounds. Sooner or later, it gives out. But then when it slides back down to, I shouldn't say slide, but when it starts to slide, it drops to a lower value for kinetic friction. So maybe it took 25 pounds to finally get that cow to move. But as soon as it starts moving, the friction drops down to 16 pounds. Don't let that confuse you. I really doubt I'm going to ask you a question about that. Okay. So sorry about that little bit of a tangent, but let's move on. And now this problem should become easy if you got that idea. So this will go a little bit quicker. It's pretty much the same thing, but with a table instead of a cow. You push a table with 20 pounds of force and it doesn't move. What's the static friction force? 20 pounds, right? Because the net force is 0. If it's not moving, it's not accelerating, and that means the net force is 0, which means friction must be matching my push. Now you push with 30 pounds and it still doesn't move. What's the friction? Yep, 3 pounds. You finally get it moving. It takes less force to keep something moving, that's kinetic friction when it's moving, than it does to start it moving, static friction. So now you are pushing with 25 pounds of force. Remember, it took 30, I was pushing with 30 pounds and it didn't move, right? But once I got it moving, then the kinetic friction drops to a lower value. So you're pushing with 25 pounds of force and it moves at constant velocity. Okay, constant velocity means the net force equals 0. So what's friction? 25 pounds. Now let's stop there for a second. If I've just now identified that friction while it's moving, kinetic friction, is 25 pounds, for the rest of the questions, if the object is moving, if the table is moving, and I say, what's friction, what are you going to answer? 25 pounds. Okay, so let's go to D. Suddenly, you push with 35 pounds. What's friction? 25 pounds. Okay, so that's the constant value that friction will remain as long as the two surfaces remain the same, as long as it's moving. If, while pushing with 35 pounds, the table has an acceleration of 5 feet per second squared, what's the mass of the table? Ooh, I just threw in a calculation problem here. So if I'm pushing with 35 pounds, we just identified what friction is, 25 pounds. So there is a net force on it. What's the net force? The net force is going to be 10 pounds. I won't worry about direction here. We know it's going to speed up because I'm pushing harder than friction in the direction that's going. And then we know the acceleration is 5 feet per second squared. Notice I'm using imperial because I'm using pounds. What's the mass? The mass is the net force, 10 pounds, over the acceleration, 5 feet per second squared. And you know me with my convenient numbers. 2, and what do you think the unit's going to be? Slugs. That's the imperial unit. Okay. just checking on time. Yeah, I'm a little bit slow here. So yeah, I said I'll do this page and then I'll do a different video maybe tomorrow night. What's the weight of the table? Okay, we threw something else at you here. Well, let's get back to an equation of the weight of an object is its mass times the acceleration due to gravity. The mass is 2 slugs. The acceleration due to gravity, which version do we use here? 32, because we're using imperial. So when you multiply 2 slug by 32 feet per second squared, you get 64 slug feet per second squared, or more simply, 64 pounds. Now you push, getting back to the question, so remember where we left off was we pushed at constant velocity, friction's 25. I push with 35, friction's 25. Now I push with 20 pounds, what's friction? 25, okay? Hopefully you get that idea and write it down in your notes. Kinetic friction remains constant as long as it keeps moving along the same surface. Nothing else really changes about it. Now you let go and it's sliding to a stop. While it's sliding, what's friction? 25 pounds, okay? Now it comes to a rest. What is friction when it's stopped? Assuming it's a level surface. 0. If you're not pushing it and there were a frictional force on it, what would happen to it? You would see that because there's a net force, it would start accelerating for no reason. So if it's just stopped there and not moving on a level surface and you're not pushing it, friction is 0. Okay, here's some more calculations. I think these are a little bit easier than the ones we did on the previous page. A ball is hitting the floor. The net force is 35 newtons up, and the normal force as drawn there is 40 newtons. Find the ball's mass. Well, this is tricky. Again, this is kind of not easy questions for a beginning physics class. So, good on you if you can get this one. So we're missing a force here that we're going to have to get to in a second. But let's go ahead and we can solve for something. Well, then we can't yet. Okay, we do need to get something here. Is what force are we missing? Because we're talking about a net force. Well, we got the normal force. The ground is pushing up on the ball. That's the normal force. But we're missing the weight, right? So the weight, I kind of made my arrow too big, sorry. We should do it proportional. If the net force is 35 newtons up and the normal force is 40 newtons up, what must be the weight? I kind of butchered that explanation. But the weight is 5 newtons. Now, once I've drawn it there, can you see how the net force is 35 newtons up? Because 5 of those are canceling the 5 newtons is canceling 5 of those 40 newtons, so you get 35 newtons up. So that was the trick. We had to find the weight of the ball by using this given information. So now that we know the weight, we know that's equal to the mass times acceleration, and it's asking for the mass. I'm telling you, this is not easy. If you do this, you are a smart cookie. So all we're going to do is take the weight of the ball and divide by the acceleration due to gravity. So the weight is 5 newtons. We're going to use the SI version. So we get 0.5, and again, trusting SI, we're going to get kilograms. Okay. 15. Okay, these will go a little bit quicker. We learned a little about air resistance. Well, except for I'm going to do a little review here. So let's go ahead and do the review. Fast forward if you don't want to hear it. I just thought some people will do it. We did a previous sheet before this, but I thought I would just show this with the answers as well, just so I don't have to draw so much. So here's the idea, the kind of the sequence of events. And again, I'm not going to have time to ask more than one question on the final about air resistance. So don't expect that you have to go through all of these things. So I don't think at that point, I think down somewhere else, I might have said what it depends on. Right there, I did say it. So maybe you want to write these down. I doubt if I'll ask something about that on the final, just not enough space, but I think you should write it down. You're going to have plenty of space on your note sheet. So air resistance depends on the shape of the object. In other words, does it have good aerodynamics, like whatever wing or whatever airplane, or is it like a piece of paper falling through the air? That's actually not the cross-sectional area. That's kind of more of what I'm saying about the piece of paper. The paper has a certain amount of surface area, but is it falling edge first or is it falling face first? So how much area is striking the wind? And 3, the speed of the object. So if it's moving faster, there's going to be more air resistance. And it's more air resistance for 2 reasons. That could be one of the questions I could ask. I don't know. I'm not going to try to give it away by looking back at the final and telling you. But those are the three reasons that affect air resistance. And for speed, it actually affects it for two reasons microscopically. If an object is moving faster, that means it's running into more air molecules every second. And every little air molecule impact is exerting a force on it. So more air molecules striking it per second is one reason why speed affects the amount of air resistance. But also, if it's moving faster through the air, those impacts are harder. There's a harder force on the paper from the air molecules. Anyways, again, I doubt if I'll ask that, but just be ready. So just running through this really quickly, I'll go back to my pointer, is let's say we just drop a ball from a start. So this is like, I haven't even let go yet. Well, the net force is just the weight on the ball, right? And remember, we now have air resistance. So this is not in free fall. And the acceleration here is 10 because since it's not moving yet, there is no air resistance yet. So technically, right when I let go, it's in free fall. But immediately, once it starts running into the air, it's no longer in free fall because there's air resistance. So keep that in mind. Free fall is just when an object is falling under the influence of gravity only, and there's no other forces acting on it. So what you see just jumping ahead, the weight always stays the same. It doesn't change. But as it's falling through the air, it's getting faster and faster. It's running into more air, and the air is hitting it harder. So what we're going to see is the air resistance force, which I'm doing F sub AR, some people just do AR, is going to grow as it's getting faster and faster. So kind of my explanations here, again, I won't have enough time to ask multiple questions on this, is notice that as it's picking up speed as it's falling, because gravity is accelerating it, the air resistance will be greater. But now what's happening to the net force? It's getting smaller because I have this resistive force pushing upwards on it. But if the net force is getting smaller, since net force is proportional to acceleration, the acceleration is getting smaller. Now don't get confused. Acceleration getting smaller does not mean slowing down. It just means it's picking up speed less quickly. It's kind of more gently ramping up its speed compared to at the beginning. But since it's moving downwards and the net force is still down, because notice the force down is greater than the force up. So if it's moving down and the net force is down, that means it is speeding up still. So a little bit later, since it's been speeding up, see my bigger motion lines? Since it's going faster, the air resistance force is growing. Now let's say it's 4 newtons. So now what's happening is since the air resistance force is greater, the net force is even smaller than it was before. Notice how we have even a bigger upward arrow, so we barely have a net force down. But which way is the net force? It's still down, right? Because the weight is larger than the air resistance. So if it's still moving down and the net force is down, it is going to be still getting faster. And something I skipped here is, since the net force is smaller here than here, the acceleration is smaller. And again, that doesn't mean it's slowing down. It just means that it's going to pick up speed even more slowly. And then here's where we get that special situation on the right, is let's say it's going so fast now that we've built up the air resistance force to equal the weight of the object. So what is the net force at this point? It is, I wrote it here somewhere, net force is 0, which means the acceleration is 0, which means it won't change velocity anymore as long as the conditions don't change. So at that point, it'll start falling at a constant velocity. It won't pick up speed, it won't slow down. So we call that terminal velocity. And the key thing there, one of the trick questions is at terminal velocity, if I get my, hope I didn't crash here. There we go. At terminal velocity, the air resistance force is equal to the weight of the object. So this is equal to that, which means it's going to fall at constant velocity. So if I told you that the ball was, let's say, a 0.5 kilogram, and I said, at terminal velocity, what is the air resistance force on this ball that is a 0.5 kilogram? Do not answer that the air resistance force is a 0.5 kilogram. First of all, is kilogram a unit of force? No. So do not say that. At terminal velocity, air resistance force is equal to the weight. So if I told you that the ball had a mass of a half a kilogram, that means its weight is 5 newtons. So at terminal velocity, the air resistance force equals the weight, and in this case equals 5 newtons. So I won't go over all this, but there's a little summary that you can kind of read there if you had to do an explanation. But again, probably one question about air resistance somewhere there. So I'm not going to ask you much. All right, back to the program. That didn't take too long. I'll finish off these questions. Some of them are really quick. Then I'll stop and maybe do the other video tomorrow night because it's getting past my bedtime of 8 o'clock. No, just kidding. Tell me the two reasons why a higher speed means more air resistance. Well, I'll just say them verbally rather than writing them. One is, as I just went over, it's running into more air particles per second. And that's where the air resistance is coming from. It's the air molecules slamming into the bottom of this thing falling. If it is falling, it doesn't have to fall. And secondly, the impacts are going to be harder. So like if you have a tennis ball being thrown at you at 5 miles per hour versus 15 miles per hour, you're going to be pushed back a little bit more by the higher speed one. So more particles per second, harder impacts. Doubt that's going to be on the final. Even these two, I doubt they're going to be on the final. But again, I don't want to promise that because I might tweak the final a little bit. The two objects are falling downward and neither has reached terminal velocity. The triangle has more air resistance, which is moving faster. Well, which one would you think would normally have less air resistance between those two? The knight, if it's falling downwards. This one right here, because look how aerodynamic it is. But somehow it has more air resistance. Not only is it more aerodynamic, there's less, what do you want to call it? I think I called it down there, cross-sectional area compared to this big thing falling down. So if somehow this has more air resistance, despite it being smaller and more aerodynamic, it must be that that one is moving faster, if that makes sense. 17, you drop 2 identical pizza boxes, so down, let's say they're both moving downwards. The first one is edge first, and the first one is face first. Which will have a higher terminal velocity? Well, which one is going to experience more air resistance at any given speed? This one, because it has a bigger cross-sectional area, it's going to be running into more air molecules. So this is going to end up reaching it's going to, how do I say this? I'm going to get more eloquent here. The idea, maybe I'll just draw this, is it has a certain weight, right? And to reach terminal velocity, the air resistance has to equal the weight. So because there is so much surface area, this will build up an air resistance force quite quickly that'll equal its weight. So it won't be going very fast by the time its air resistance equals its weight. Meanwhile, with this one such a small cross-sectional area, it's going to have to go a lot faster in order to build up enough air resistance to equal its weight. So sorry that my diagrams don't make sense there, but it's just the idea that with such a little cross-sectional area, to build up an air resistance equal to its weight, it has to go faster. Now, if you had to answer that one, common sense. You've dropped things before. You probably dropped a pizza box, edge first or face first. Which one will have a higher terminal velocity? Well, the edge first one. Okay. I told you I'd go faster, but I didn't. 18, you drop a clay brick and a lead brick, assuming you know the lead brick is heavier, both of equal size and shape. But the lead brick is 6 times denser, so it has 6 times the weight, assuming, again, that they're the same size, have 6 times the weight. How much more air resistance does the lead brick need to reach terminal velocity compared to the clay brick? Well, it needs 6 times more because, again, to reach terminal velocity, the air resistance has to equal the weight of the object. So assuming that the lead brick is same size, but therefore 6 times the weight, it'll have to have 6 times more air resistance. So which will have a higher terminal velocity? Oh yeah, the lead brick, because it will need to go really fast to build up 6 times more air resistance than the clay brick has. Okay, so let's do some more of these. And again, maybe I'll ask 2 of these. I don't know, there's so many, but like I said, I'll probably have 15 or 16 questions on the final on this unit. So I'm not going to waste like 4 questions on air resistance and terminal velocity. As you drop a ball, as it's falling, before it reaches terminal velocity, what happens to its speed? Well, it's falling. Gravity is, again, when we haven't reached terminal velocity, it's speeding things up. So the speed's going to increase. So what happens to the air resistance on the ball while it's increasing speed? It's going to increase. The faster something moves, the greater the air resistance. So what happens to the net force on it? The net force decreases because on the ball, you have this constant weight that's not changing. But as it's falling and getting faster, the air resistance force is getting bigger, bigger, and bigger, and bigger. So the net force is getting smaller, smaller, and smaller. So if the net force is getting smaller, remember net force is proportional to the acceleration. If the net force is getting smaller, the acceleration is getting smaller. And then this is what I said earlier. That does not mean that it's getting slower. It just means it's going to pick up speed less quickly. It is still accelerating and increasing speed, but it's just not accelerating at such the great rate that it was earlier. Okay, jumping to terminal velocity, how does the air resistance force compare to the weight at terminal velocity? Same. What is the net force on the ball? Well, the net force is going to be zero. Because if those are the two forces acting on it and they're the same, the net force must be zero. They cancel each other. What's the acceleration? Well, if the net force is zero, the acceleration is zero, which means it's not going to change velocity. It's going to fall at constant velocity. Oh, here's my trick question. So just so you didn't have to do a calculation, I'm giving you both the mass of the ball and the weight of the ball. That's 0.1 kilogram, which means multiplying by 10, its weight is 1 Newton. So what is the air resistance force at terminal velocity, given those two options? 1 Newton. Again, the air resistance force is equal to the weight of the object at terminal velocity, not its mass. Now, again, I don't know if I'll ask this. I don't have many questions that I can ask on that unit. On the unit test, I certainly did. This is kind of a tough one. I don't know if I'd ask this. It's a little tough. I could ask questions like this with graphs for free fall, which I did on the last review sheet, if you go review that one. But with air resistance, it's a little trickier, but let's go ahead and do it. If these are velocity graphs, so they're all v versus time, negative is down, which can represent that of an object falling through the air until it reaches terminal velocity. So we could analyze what the motions of each of these means and see which matches what such an object would encounter, but let's go backwards. Let's think about an object falling down until it reaches terminal velocity. It's going to start out fast, right? Because it doesn't have any air resistance on it. But what's going to happen is it's going to slow down, right? And finally, it's not going to slow down to a stop. It slows down until it's a constant velocity. So we're looking for something moving downwards in the negative direction, and they all are, because we said down is the negative thing. So they're all moving down. Even this one over here is moving down. Because it's all in the negative velocity. These are velocity graphs. So they're all moving down, but which one shows you something that as it's falling, it is getting, the acceleration is getting smaller. Actually, I screwed that up. I told you I was not going to re-record this, and I'm not going to. It's just my lack of precise language there. I knew what I was thinking, but by saying slowing down, totally wrong. So if you saw that, good for you for catching me on that. It starts out fast, and it is picking up speed. This is very important. That's why I paused and realized I'd said something wrong. So it's picking up speed. It's just that it's not picking up speed as quickly. And I just made that mistake. I think I did. My brain, I knew that wasn't it, but I think the way I said it was totally wrong. Back to 19E, it's not slowing down. It's still gaining speed, but just not gaining speed as quickly. So if you were probably smarter than me on that one. So anyways, we're looking for something that is picking up speed, getting faster, but just kind of gradually picking up speed. So for example, this one can't be it because it's picking up speed. It's getting farther from the zero, so it's going faster and faster and faster, but it's the same acceleration. I'll just get to the answer and then we'll see why this one's not right. This one is getting faster, but look, as time progresses, it's not picking up speed as quickly, and it does this. Oops. I didn't mean to draw that little line. Does this mean once it reaches this and a horizontal, does that mean it stopped? Well, on a position graph, it would, but on a velocity graph, that means that it is constant velocity. So this is the right one, that it's moving downwards and picking up speed, But as time progresses, the slope, which is the acceleration, gradually decreases, which means that it's picking up speed more slowly. The acceleration is decreasing. This is not it, just because why would it have kind of a constant acceleration? Then boom, suddenly right here, it changes to a constant velocity. Doesn't make sense. And this one shows over here something that is moving downwards, but slowing down, slowing down, slowing down, slowing down until it reaches zero velocity. So that's not it. Yeah, just as you can tell by the fact that I screwed up my explanation, I'm probably not going to ask that on the final. 21. Some easy questions. We'll call this video a wrap. I'm already well over an hour. I'm 4 times more massive than a second grader. He isn't looking where he's going and runs into me as I stand there. So I'm just standing there and he runs into me. How does the force he exerts on me compare to the force I exert on him? Back to the third law. Equal and opposite. So same force. But who will accelerate more? Well, your acceleration depends on the force on you and your mass. So we both exert the same force. If he runs against me with 30 pounds of force, I'm pushing on him with 30 pounds of force. So we both experience the same force, but who has more inertia? Me. So I'm not going to accelerate very much. So the kid will have more acceleration, not because he has more force on him, but because he has a smaller inertia, which allows him to accelerate more. All right, let's do this last third law one, and then we'll call this a wrap to this video. You push against the wall with 20 pounds. Oh, this is like what I was talking about earlier. So again, I didn't structure this well. I'm actually doing an easier one later in the worksheet. You push against the wall with 20 pounds of force. We call this the force of hand on wall, or we could call it that. How hard is the wall pushing on your hand? Well, 20 pounds. That's the whole idea in a nutshell of Newton's third law. You weigh 125 pounds. We can call this force of earth on you. So how hard are you pulling up on the earth? 125. Now I know it's easier just because I'm not giving you other options of numbers, so it's got to be the same thing, but I hope it makes sense. You jump up and then slam your feet on the floor, exerting a force of 200 pounds. We call this the force of you on the floor. How hard is the floor pushing up on you? 200 pounds. You see how they're like mashed together? However hard you're pushing on the floor pushes up on you. And that's the normal force. In physics, what do we call, I just gave it away, call this force of how hard a surface like the floor pushes on something? The normal force, which we symbolize F sub n. So if a ball that is slamming against the floor has a normal force of 5 pounds acting on it, how hard is the ball pushing down on the floor? 5 pounds. Okay. I know we have another third law thing there, but again, I'm just going to cut this video short and do a second video later. Maybe I'll still do it tonight. Thanks for listening.